All right, 9.6 linear programming. This is right out of your notes. It's a process system of linear inequalities and using the region's vertices to produce the optimal output in an objective function. There's my lesson. Any questions? That's what you're going to be doing. All right, so what does all that mean? So we're trying to figure out a solution to some scenario. It's kind of like 9.4, where 9.4, the partial fractions, has a whole bunch of different subproblems. 9.6 is the same. It's a whole bunch of different subproblems. A lot of them are story problems, and we're trying to solve a system of inequalities eventually. Okay? So from the story problems, you're going to be creating a system of linear inequalities. So the next example, it'll be a story problem. So that's a lot of the difficulty, is setting these up. But assuming that we set those up correctly, and we have some sort of a objective function, which is right here in this case, we're going to minimize the cost. Okay? So we've got inequalities, means they're greater than or equal to. They're not equations. They're like less than or equal to or less than, which means you're going to be shading. We're going to solve that system, and from that system plug in vertices into our objective function. Okay, so how do I graph 3x plus 4y greater than or equal to 32? Yes, you're going to have to graph a bunch of lines. Remember how to graph lines.
Yes.
Yeah, that was not rhetorical. Yes, very good. So one way to graph a line is just to always just solve for y. Okay, so subtract 3x, divide by 4, and we have it in slope-intercept form. My y-intercept is 8, and my slope is negative 3/4. Okay, so that line, is it solid or dashed? Do you know? I don't know how long it's been since you graphed. It is solid. Do you know why?
Because it's less than or more than or equal.
Very good, because there's that little dash underneath. If it was just y is greater than, then it would be dashed. Since there's a line underneath it, then it's solid. So that y equals negative, or is y greater than or equal to negative 3/4 x plus 8 is right here. It's got my y-intercept of 8. I go down 3/4, down 3/4, and I graph that line. So now I have to figure out which side of that line to shade. So what I do, the way I teach it, is you pick an ordered pair that's not on the line. I always choose 0, 0 if possible. It's just the easiest ordered pair. So looking at this, if I plug in 0 for x and 0 for y, does that make that inequality true? Is 0 plus 0 greater than or equal to 32?
No.
Okay, you shade the true side. You do not shade the false side. That 0, 0 is false. 0, 0 is right over here. This was our line. So this whole side is false. So everything on this side is going to be shaded. So graphing this inequality, same thing. I solve for y. Y is greater than or equal to negative 1/4 x plus 6. Has a y-intercept of 6. Slope of negative 1/4. That's this one. And then also false. Okay, I'm all over the place here. So 0, 0 is also false, so I shade above it again. Okay, the last two inequalities, x is less than or equal to 12. That means x equals 12 is right here. It's got to be less than or equal to 12. Y is less than or equal to 15, so that's this horizontal line. It's less than or equal to that. Okay, so we have this shaded region. You have all of these vertices. That's what I mean by vertices, the corners of the region. All 5 of those are where the objective function will have a solution. It will not be on anything except a corner. So we have 5 possibilities. So we have 5 possible vertices, and you plug each of them into your objective function. The objective function is c equals 5x plus 4y. So we plug 0, 15, our first one in, and all of these into our function, and we're trying to minimize it, so it looks like a minimum is right there. We get 60, 32, 40, 72, and 120. That's where our minimum occurs, 0, 8. So our minimum is 32, and it occurs at 0, 8. That would be our solution. Now that doesn't really make any meaningful sense because we didn't have a story problem. But if this question asked, how do you minimize the amount of cost and what will the cost be, you might create 0 items of the first and 8 items of the second. In total, it's going to be a cost of 32, and we'd minimize it and still meet the parameters or the constraints of the problem. All right, so that's how to do these if it wasn't a story problem. I'll give you one story problem today. That's probably all I have time for. In our notes, kind of walk through it here. Again, it can be difficult pulling out the information from the story problem. And after that, we graph our inequalities, we shade them, and use our vertices in our objective function. All right. Piñatas are made to sell at a craft fair. It takes 2 hours to make a mini piñata, 3 hours to make a regular size. Okay, so already I see two variables. I say X is number of mini piñatas, and Y is the number of regular piñatas. Okay, it takes 2 hours to make mini and 3 hours to make a regular. That's the amount of time. We're going to use that information in our time inequality. Okay, 2 hours to make mini, 3 hours to make regular. Well, how much time do we have total? No more than 30. So our first inequality will be 2 for every mini, 3 for every regular, has to be less than or equal to 30. You make an inequality for the hours. 2x plus 3y is less than or equal to 30. Okay, I wrote hours there because it's hard to figure out if it's going to be a cost thing or a time thing. In this case, all of this has to do with the amount of time. Okay, the next one. The owner of the craft booth will make a profit of $12 for each mini piñata sold and $20 for each regular piñata sold. They don't really give us information in order, but that right there, if you hear profit, a lot of times that'll be your objective function. So our objective function is right there. Our profit is going to be 12 for X1 and 24 for the Y1. So 12 bucks for the mini, 24 for the regular. If the craft booth owner has no more than 30 hours available, we already used that. To make the piñatas, we want to have at least 12 piñatas to sell. Oh, at least 12 piñatas to sell. So we need at least 12. Well, X is the number of minis, Y is the number of regulars, so X plus Y has to be greater than or equal to 12. We need at least 12. So those two added together has to be greater than or equal to 12. And then how many of each piñata should we make? We know we're going to have at least 0 and 0. So those are all of our inequalities. Now it's like the previous problem. We graph them. There's my shaded region. I only have three vertices. We plug all 3 of those into our profit equation. And looks like I get $216, $144, and $180. So $216 is the most profit we can make. That would be using 6 minis and 6 regular piñatas. Okay, there's no way you could completely understand this with just watching me go through that. You have to do the problems. So tomorrow we will kind of plow our way through it, and you're going to be doing the problem. I'm not just going to be like talking my way through it. Okay? But what questions do you have right now? It's not all that engaging just to watch me like talk about something. You have to do it. All right, we'll learn more from tomorrow's lesson.